Okay. Right. Assalamualaikum warahmatullahi wabarakatuh and good afternoon, everyone. Thank you for joining the class today. So this week is week 9 already. Okay. As I promised in the WhatsApp conversation this morning, we are going to discuss, or we would like to know more about ANN, because the next talk will be the speaker will talk about deep learning. So I don't want you to, feel left out without knowing the principle of ANN. Okay, so without further ado, let me see first. I have shared the slides with you so that at least you can have a view about um, my slides. Okay, all right. Okay, so you can see my slides now. All right. So basically, I think most of you have heard about this term ANN. So the definition is ANN is a computing system made up of a number of simple, highly interconnected processing elements process information by their dynamic state response to external inputs. So in brief, we know that NN needs input and you need a decision or processing element uh, in the middle, and at the end you have output. Okay, so all these input and output are interconnected by the element at the middle. Okay, so probably you have seen this model or architecture. We call this ANN architecture. So when your examiner asking you, or maybe in the future, people ask you which ANN architecture or which ANN model that you use, meaning that we are talking about these elements. Yeah. So first element or first stage in our ANN is the input layer. So input layer, uh, if you are talking about ANN, basic ANN, it's actually the list of feature, matrix of features. So if you can, let's say we use examples of fruits. Last week we give example if we would like to classify between orange and apple, let's say shape, color, and texture. So shape, color, and texture are features. So when we do image processing to the image of orange and apple, we can extract value, numerical value from the image. So we can have and we can store them as metrics, and this will be called as input layer. Okay, so that three features. So meaning that, let's say we have only three values extracted from that three features. So three values that will be representing one input. So if we have many pictures or many images, let's say 200 images, so 200 multiplied by 3 because we have three features, so 600 information will be at the input layer. Okay. So in the middle, or most of the time, people calling it as a black box. So this is what is the content of the black box, is the hidden layer. Okay, inside the hidden layer, actually we have nodes. Okay, these nodes, what is this nodes doing is connected to the from input to the every single node in the middle. So every line here, okay, let's say this is input 1, this is input 2. So as you can see, input 1 has line connected to node 1 in the middle, node 2 in the middle, node 3 in the middle. Input 2 connected to node 1 in the middle, node 2 in the middle, node 3 in the middle. Okay, so here we call it as hidden layer. So this is neuron 1, neuron 2, neuron 3. Okay. So in on this line, okay, every single line that is represented is this in this diagram is your weight. Okay, so this weight is actually um, is variable or the parameter that will multiply with your feature value. Okay, so feature value multiply by your weight. So it will construct a matrix here too. So how are you going to decide, or how are you going to get the output from one neuron is you sum up all the information going into the neuron. Okay, so x1 multiplied by width 1, x2 multiplied by width 2. Okay, so you sum up, and then we will have the activation function. So the one that is represented by this like a sinusoidal um, graph. So this is activation function. So when we sum up the value, that value will be input to the our activation function. Activation function will produce output from the neuron. So let's say we have 3 hidden neuron here. So we have 2 variables or 2 values add up, then we get the output. So one output from neuron 1, one output from neuron 2, and one output from neuron 3. And the process will be repeated again at the output layer. So since we have 3 lines coming into the output layer, so we will have the output from neuron 1 multiplied by with 1 here, output from neuron 2 multiplied by with 2 here, and output from hidden neuron 3 multiply with the weight 3 here. We sum up these 3, and then we will apply the activation function here again, and we will get a single output. So basically, this is the architecture model. So when you look at it, it's actually more or less it's just multiplication of matrix, because how many inputs you have, how many lines or weights that you have, and then what are how many neuron that you have in the hidden layer. So all this, it can be represented by a equation, by an equation to sum up everything. So during the training, okay, during the training, what you want to obtain is you want to finalize every weight line in the architecture. So for example here, weight 1 here, it can vary from 0 to 1. So it can be 0 0.13, 0 0.63, 0 0.22, 0 0.18. So the training is trying to test all the weight values, with all possible weight values, in order for you to get uh, the target output. So target output meaning that let's say the first input, let's say it is class A, this one is class B. Yeah. So meaning that when you insert something, you get exactly the same as the label, which is this is class A, so the output should be class A, meaning that you get the target value. So once you are able to do that, meaning that the weights that you have identified here, activation function that you select here, and the weights that you get here are good. They are correct. So your training is already complete. Uh, so training is to obtain all the weights value. We would like to finalize the weight values and the activation function in order for us to get the exact results or the least error. Okay, so there are your goal can be to achieve the target, or you want to minimize the error. Okay. So basically, this is the diagram that you have to remember. Okay, it can be simplified more, but this is something that much easier for me to explain rather than too basic or too simple. Maybe you cannot see the relationship between the input layer, hidden layer, output layer, the weights, and activation function. Okay. You can stop me anytime if you want to, because I think this is one of the basic principle that you want to know. That's why you join my class. Okay. So NN is actually a model of brain and nervous system. That's why actually like what we brain are constructed of. So we have the neuron and we have the synapse, the connection between one neuron to one neuron. So it is actually triggering the connection. So the more the synapse is activated, or in terms of ANN, if the weight value, okay, the weight value here is bigger, meaning that near to 1, because we have reached 0 to 1, yeah, let's say 0.97. So meaning that this weight value is very high, meaning that this line is activated. Okay, if your weight is 0.001, so meaning that this line is not activated, or maybe there is no connection to this hidden layer number 3. Yeah. So um, so NN is learning. Okay, it's actually very simple principles. That's why what you can see nowadays, there are so many toolboxes whereby you can just run your data, and as long as you know that your data is enough, labeled correctly, and you know what is the output that you want, then you just can make use of any of the tools. Yeah. However, it has very complex behaviors, because sometimes when you have so many hidden layers later on, it's going to be very complicated for you to derive that mathematically. Okay, so and sometimes when you have the data, new data coming in, um, uh, i- and if that data is very rare or very kind of outliers, so it's gonna be hard for you to explain why that rare data or outlier data will produce such output. Yeah. Okay. So this is something like what we have heard of before. Okay, and I mentioned that machine learning has a few subsets. Uh, but here we are talking about branches. Okay, we have the unsupervised, we have supervised, and reinforcement learning. So most of the image classification, they are falling under supervised learning, because meaning that they are trained with the label data and tested with the label data. Okay, um, so then we normally measure the errors and measure the accuracy of the classifier. Okay. Right. So what does NN consist of? Okay, so if we are looking at the previous diagram, or you may refer to this simpler diagram, you have the input units. Okay, so what if we are talking about ANN, it's features. If we are talking about CNN or deep learning, it's actually the raw image. Okay, the matrix of the images in the with the values of the intensity. So input, um, if you are talking about features, normally we are only dealing with numerical value. So if you are asking me how actually a speech signal can be represented as the input unit. So that's why we do pre-processing to the speech. So for example, one of the method is using MFCC. Okay, what is Bernard doing now? Whereby you are converting the whole signal of audio, okay, the histogram that you have, or the waveform that you have. Because when you have a waveform, you don't know what are the value that you are looking to. So what we do is we simplify that signal or the waveform into probably 12 variables or 12 coefficients, and that 12 coefficient will represent one single waveform. Okay. For image is very clear, because it is actually in a digital form, whereby you have a matrix of it and then represented. If you are talking about grayscale, so it's going to be 0 to 255, or it can be a black and white image, so you have 0 and 1. Okay. Mm, Other data, sensor data, they are numerical values, so you don't have to do any pre-processing to it, unless you have to do the cleaning, or probably you have to normalize the data in case that the transmission of data or sensor is not is not synchronized. So you may have missing data or outliers, something like what Dr. Sharifa has described last week. Yeah. So the input. So the input is the most important part because you need to know is the value will be able to be inserted to the model, ANN model, and will there be any pattern that can be observed by the network in order for you to do the classification or to do prediction. So the output unit is the opposite side of the network. Okay, so output can be the classes, can be the groupings. So if your output is between class A and class B, so you will have two nodes here or two circles here. If your output is only one, so you will have a single node. So if, let's say you want to classify uh, the numbers, handwritten numbers. So you will have 0 until 9. So you will have 0 until 9. So more nodes, 10 nodes for the output. So hidden unit is between the input and the output. So what you see here is a very simple one. Sometimes it can have one layer. So this is single layer, double layer, third layer, fourth layer, and many, many more layers. So one layer can have 4 neurons, okay, like this, okay, or maybe it can only have 3 neurons, maybe 2 neurons, or even 1 neuron. So we call it single perceptron. Yeah. So most neural network are fully connected. So as you can see, as I mentioned before, your aim in training is to find the weights for every line that you have here. So the more input you have, more nodes, meaning that you have more lines. The more neurons you have, meaning that you will have more lines and more output from the neurons going to the output layer. Okay, so everything must be fully connected. There is shouldn't be any missing line to it. That's why when you look at the programming side of it or tools, you need to ensure that the metric size of the input and the metric size of the output will match. So you have to look back at the principle of matrix multiplication. So for example, here, 2, uh, 2, 2 by 3, okay, say 2 by 2 times 3 by 3, so your output should be 2 by 3. So how so it should be match input to the output because everything will be multiplied using matrix concept. So the weight, okay, the weight is the one that represented by the line. There are the connections between one unit and another, okay, represented by a number which can be either positive or negative. Okay, so normally most of architecture they are using positive numbers. Yeah. So the higher the weight, the more influence one unit has one on another. So as you can recall from this diagram, because why we are saying that if you have higher weights value here, you will influence because you are going to sum up the values, okay? Input one with one and input two with two. Here you sum up. So when you sum up, and if this weight value is higher, meaning that the summation will be biased to this value, and meaning that it will influence the output. Okay, so that's the meaning of if you have higher weight value, it will have a higher impact to the output rather than other units. Okay. So how does a neural network learns? Okay. There are two ways of information flows. Something that we heard from last week also. We have feed-forward network, meaning that everything will be going towards from input to the output. And this one is on recurrent neural network or back propagating, meaning that from input up to the output. the one that you get from the output will go back to the input. Okay, let's see. Okay, here. So this is a feed-forward neural network, meaning that whatever output that you obtain here, you will only compare it with the label, meaning that you know, let's say the error that you aim for is 0. And once you get the weight value here in the first trial, okay, and you get the error is 0.5, meaning that you still have higher error. But because this is a feed forward, you don't have any idea which weight value that is actually totally wrong or divert from the ideal one. So what feed forward will do, they will just randomly change the weights value, and as long as it's changed from the previous run. So in the second run, they just change. Maybe previously it was 0.1 here. This time it increased to 0.3. This one maybe previously is 0.16. So the next one, it can be 0.57. So there is no idea, no clue where is that that weight value is going to, until they get the error and then say, okay, the error is increasing, rather than before it's 0.5, now it's 0.57. So it keeps doing the changes to the weights without having idea where are they going to near to better error or worse error, because it's feed forward. Compared to the back propagation, once you have all the output, your output uh, will be, the information about the error will be propagated back to your weights, meaning that um, you know that previous error, let's say 0.5, now you want it to be going to at least near to zero point 0.4 to improve the performance. Okay, so um, w- with that hint or with that information, so the weight will be modified accordingly to the direction in order to reduce the error. So they are not just, keep changing without any idea, just change randomly. No, this one is much more strategized. Okay? They are changing the weights, but in the direction that goes or with the aim to reduce the error. So this is still with the hidden layer, 3 neurons, hidden layer, 2 neurons, but this one, um, uh, um, it has only one layer. So meaning that actually it should be here, yeah. One single neuron, or we call it single layer perceptron. Um, so to summarize, the the model must have processing units. Uh, we have activation function. So in every neuron, so we have it in the hidden layer. Uh, we have it in the hidden layer, and we also have it at the output layer. So we will have the activation function. And then function to use to compute output of processing unit. So this is at the output layer, how to interpret the results. And then pattern of connectivity, meaning that all the arrows or the weights, the rule of activation propagation. So how are you going to process any summation value and to decide um, the the results, and also how are you going to pass it back to the weights, and the rule of learning employed. Okay. Okay, all right. So oh, sorry. So what is the purpose of the activation function? Probably when you look at the previous diagram, you don't see what is important, and yet there are various choices of activation function. It can be sigmoid, it can be tan, it can be relu. Okay, so those are the activation function, and normally it's already mathematically modeled or calculated in order for you to achieve the output that you want. So So let's say we have a single neural model, okay, meaning that only one perceptron, and our function, activation function, is fx equals to x. So if you look at this, okay, uh, so we have to input x1 and x2. Okay, um, this is actually the 1 and 0. Okay, let me see. Okay, no, this is to divide the to classify the input. Okay, so that you know that these are the group of x2 and these are the group of x1. This one is also one side and a two side. So normally when we have this linear line, okay, it is using one single perceptron. So something like what you have as a threshold, okay, threshold value. But if you have this kind of cases, do you still remember SVM last week, whereby the distribution of the data, okay, it's not, this is non-linear. So meaning that you cannot rely on one single line to divide the data into two groups. So when this thing happen, we need nonlinear. So function fx equals to x is not able to do the classification of this kind of data. Okay. Uh, since our speaker is already logging in, okay, I just skip few things. Okay, so these are examples of activation function. Okay, so if you are doing fx equals to x equals to 1, if x more than 0, or 0 if x less than 0, so what you get will be the threshold function like this. So you remember that before we go to activation function, we have to sum up the weight 1 x1 plus weight 2 x2. Okay, so the summation of that two will be your x. Okay, so if your x more than 0, so your output will be 1. So the value that will come out from your hidden neuron, okay, is 1. Mm, let me see. Okay. 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 So you remember that our neuron, right? So let's say this is x1, x2. So x input 1, okay, input 2, okay, with 1, with 2. Okay. So you multiply these two and then you sum up them. Okay. So after you sum up them, then you have the activation function. So when you sum up them, the summation is equals to x. So when you, let's say in that neuron, you use the threshold function, you just compare what is your x value. If your x value is equals to 1, more than 0, then what you get is 1. So before, so this is, let's say this is your output, yeah, output layer. Normally we call it y. Okay, so the value that will come up from this neuron is 1 because of the summation, and then you apply to threshold function and you got 1. So every single activation function will produce different output. So this time, for example, here, if yours is 0.5, so the output will be a little bit different. It's not 1, but maybe 1.5. For this case, what is your x, exponential of x here? So when you apply sigmoid function, so your value of fx or your y will be, this value will be maybe 0.8, for example. So different activation function will produce different, let me stop. Okay, should be, oh, sorry. let me clear the. Mm, Okay, so every single one will produce different output at the output layer or next. If you have many layers of hidden neurons, hidden layers, so you will have output from that single neuron will be differently. So there is no rules saying that you must apply same activation function to all neurons inside your model. No, no rules of that. So maybe your first neuron you use threshold function. The second one you use sigmoid. The other maybe you use what else that we have here? Okay, maybe we have a binary step and then arctangent, maybe ReLU. So as you can see here, the pattern of your output will be totally different. Yeah. How are you going to decide on that? You have to test your data, run the training. So from there, maybe you can see the pattern of your output. Is maybe divert a little bit, maybe it's not really there. So you will get the idea what kind of activation function that you can use. Okay. All right. So okay, just ignore this one. I forgot to um, I forgot to delete this one. However, this is one of the problem that is non-linear. Okay, so um, what this slide shows is how actually the process can be done manually. Okay, so as you can see, the values here, the values of weights here, they are decided manually. So we just try it to give the so that you can experience the process and the calculation involved. So as you can see here, the first hidden neuron, uh, the summation of the input, okay, will be 1.3 and 0.8. And then let's say we apply sigmoid function to it. So sigmoid function of 1.3 and 0.8 will produce the different value to it. Okay, right. And then we also have weights that have from the hidden neuron to the output. So now the output from sigmoid multiply with the weights here, and then we sum up everything. We got 1.2, sigmoid of 1.2 is 0.7. So that is our calculated output. And yet our target is 0, for example. So it's still far, far away for us to achieve 0. So we will repeat the process again. We tweak, change the value here and everything. Maybe we just keep the sigmoid function and then we rerun it many, many, many times. Okay. So the iteration of this, what we call in your tools normally is epoch. Right. Okay. I think basically that's the idea of a neural network. That are the components that you have to know. Okay. Um, Limitation. Probably you can read this yourself. I also include the video on of a better explanation, maybe if you need it. And then I also include extra additional references. Okay, these are some of the examples. Um, uh, Maybe later I will give you the problem that you have to solve using machine learning. But this one is these are the examples of exercises that we have done in class. Okay, we are trying to classify lorry and van using the features of mass and length, and they try to run it using Excel at first, and then they tweak it manually by hand, and then they experience that when you tweak it manually the weight, and then you realize that sometimes you are repeating the same weight value without you realizing it. So now you know to do it manually. Yes, you can do it, but there must be a systematic way for you to do that in order for you to achieve accurate results. Yeah. Okay, I think okay, this is also some info that I would like you to explore. That's why I highlight it here, because it's using C++. Probably it's gonna be much easier for you to understand the concept when you look at the program itself. Okay, you can see the code line by line. Okay, okay, all right. All right. Do you have any question with the ANN? I try to simplify the concept as simple as possible, because I think it is there. Okay. The challenges is because ANN or machine learning, they have various architecture. Okay, so you will heard or you will read more bombastic word, not not the ANN that I introduced today, because this area is evolving and keep changing every day. So many people trying to improve the architecture, many people saying that their models are better and better. So, but more or less, they are fundamentally, they are based on the ANN architecture that I have described before. So the changes may be on the hidden layers. The changes can be from the activation function. It can be from the training method. It can be from how you measure the output and how you optimize the way for you to search for better parameters. Okay, when you search for the parameters, especially weights and activation function, sometimes it's too massive, the data is too massive, the pattern is too complicated, and then you don't have idea where to start or when to stop. So that's why we will need an optimization method for that. Okay, all right. Let me see, Umi is in. Umi,
Yes.
okay,
Okay.
all right. Thanks, Umi.
Okay,
Sorry,
welcome.
Umi. I'm just dragging a bit there.
Tak apa, it's okay.
So basically they already know the basic of NN. Okay. So for class, so this is our next speaker. Okay, she has been involved with deep learning for many years. So even today, she will share with us her PhD project. Okay, she is my PhD student, but she had also involved with data science a lot. So that's why I invited her to be to share her knowledge and experience for class today. Okay, so without further ado, I would like to invite Madam Umi for presentation. Umi, can
Yeah.
you able to share, ke? Is it? Okay.
Jap try.
I already allow multiple participants.
Okay.
For the class, you don't have to be very quiet. You can just ask question. It's not, you are not every day you can listen to the speaker sharing about knowledge on ANN. Yeah, maybe you can see you can watch YouTube, but you cannot ask question in real time. But today you can ask question in real time. Okay. By
Yeah.
the way, Ame Zuhair, me.
Yes, yeah.
Yeah, so this is the sifu that I am referring to for your question
Oh,
about deep learning. Okay, so maybe today
okay.
if you have any additional question on deep learning on your tools, probably you can ask Madam Umi for that. Yeah.
Yes, you're welcome to ask.
Okay.
Okay. All right, Umi, please.
Okay. Boleh nampak skrin ni?
Boleh.
Okay, okay. Alright. Okay. Sekejap eh.
Umi tak dengar. Tak dengar.
Dengar tak?
Okay.
Okay. Tadi termute kot.
Ah,
Okay. Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to everyone. So harap bersemangat lah. Ada foreigner
Ada
Okay,
foreigners.
okay. Hope you keep positive not getting sleepy. Okay, so my name is Umi Kalsom. So I am PhD student under supervision of Dr. Sham. Okay, so I will share my PhD research. Okay, my title of research is classification of pH negative myeloproliferative neoplasm based on deep learning technique. Okay, before that, let me share a little bit about my academic background and working experience. So I am graduated in bachelor. My degree is medical electronic engineering from UTM Skudai. Then I further my master in computer system engineering, and currently further my PhD in biomedical engineering in UPM. Okay, so for my working experience, I work as a biomedical engineer. So I'm working. I started my work after master, not directly after bachelor. So I started my work after master. And after that, I take data scientist certification. And then I following by the certification, and then I work as data scientist at UAM Magenta Berhad. Then I got another offer as a senior data scientist, and then another offer as a senior data analytics. So currently at my current company, Sandabi Property. Okay, that's all about my background. So we go back to the study. Okay, this is the outline of my presentation. As usual, we have intro, literature, problem statement, objective, method, result, and lastly is conclusion. Okay, for any of the data science problem or any issue that we want to solve, so we need to know the domain. So domain for my research is medical. So I need to go through first what is the disease that I need to solve. Okay, for now is MPN. So what is MPN? So MPN is myeloproliferative neoplasm, or we refer it as MPN. So it's a group of disorder which the bone marrow stem cells grow and reproduce abnormally. So it can possibly because of the excess number of red cells or white blood cells or platelet. So previously, MPN were called as myeloproliferative disease until, and then they revised, WHO revised the terminology after they observe actually the disease has poor prognosis, and then it can convert to another disease that very poor. So it changed to myeloproliferative neoplasm, which is one of cancer type. Okay. We have several types of MPN, but in this study, focus on the three classical type, or we can say as the most common type of MPN occur. Okay, first is polycythemia vera, or PV, and then we have essential thrombocythemia, ET, and then primary myelofibrosis, or PMF.
Yeah, me. Probably.
Yeah,
Did Umi mention this is on blood disorder? Blood disorder problem, something like. Probably this part MPN is not very familiar. Maybe what is more familiar like leukemia.
Yes.
Okay. So leukemia is also one of the blood disorder.
Blood cancer.
Blood cancer. So MPN is also subset of it. So it's also blood disorder that can leads to blood cancer.
Yep. Actually, for the MPN also can lead to the one of another type of blood cancer with more poor prognosis lah. Okay. Okay, for diagnostic investigation of MPN, we need integration actually of the different modalities. For example, we need complete blood count, and then we need full blood count, and then peripheral blood smear, and then bone marrow biopsy. And currently we have more advanced to diagnose. We have molecular genetic analysis. However, we only focus on the bone marrow biopsy in this study. Okay, this is the example of normal bone marrow biopsy. So semua hari ni everyone in this class will attend medical class lah. Okay, So it shows trilineage hematopoiesis, which has three major cell lines are represented, which is myelomonocytic cell, erythroid cells, and megakaryocytic cells. It refers actually to the white blood cell, red blood cells, and platelet. Okay, this is the example of bone marrow biopsy. For normal architecture, it shows normal cellularity and architecture lah. The composition is normal. Okay, but for the PV patient, it shows increase in myeloid, erythroid, and megakaryocytic cells. So we can see the image is hypercellular. It's more like we have more element in the slide. Okay, and then for the ET, we can see increase in size and numbers for megakaryocytic. Megakaryocytic is here, the bigger cell in the blood cell. And then we have for PMF, this is example of the fibrotic stage of PMF, which is the normal marrow has replaced by the fibrous tissue. So it has fibrous tissue here, like it's not normal like it's circle or round shape of the cell. Okay. For the problem statement number 1, okay, MPN are characterized by abnormal proliferation of mature bone marrow cells. However, the characteristic is overlap. So it needs integration of numerous diagnostic modalities for accurate result. So for example, I mentioned before, we need to clinical evaluation, and then we need histological assessment for bone marrow image example, and then we need to expanding molecular genetic data. So however, WHO stressed out that in the latest revision or latest reference to classify the MPN, bone marrow morphology is fundamental importance to distinguish between MPN. Okay, for the second problem statement is bone marrow evaluation is highly dependent on clinician and pathologists to assess the disease persistently. However, the evaluation is suffer to substantial inter-observer variability because the observation is very subjective. So it exposed to risk of misdiagnosis and mistreatment. So we, in deep learning, we have feature learning, which is I will explain later. The feature learning part, it has ability to extract important information from input data. So our input data is here is image by bone marrow biopsy image. So it can help to reduce dependency to the expertise and also less human error. Okay, for the next problem statement is deep learning, however, despite of the good performance or promising result, the underlying theory is hard to interpret, and some people say it's like a black box theory. So we don't know, we cannot interpret it very clearly. So if you are using this model, we need to evaluate the model using performance metric thoroughly to justify the reliability and robustness. For example, we calculate the accuracy as the common performance metric lah, accuracy, F1 score, precision, recall, ROC, AUC curve. Okay, and for the fourth problem statement or the last one. Okay, despite benchmarking model, for example, we have deep learning that developed by Google, has successfully developed, deployment into clinical practice was found very limited. Okay, perhaps medical community are unable to perceive concept of AI because the language or the concept is different. So it's not understandable by the community. So the classified disease using real data from hospital with confirmation of diagnosis by the pathologist and clinician, hopefully it can help to translate from research to clinical practice. Okay. Next, we go to the objective of the study. First, we need to identify distinguished morphology of bone marrow biopsy for the three types of MPN, and then we construct the learning algorithm using deep learning, and then we assess the performance of developed model based on evaluation metric, and then finally we validate the finding of the study by comparing the detection output with the clinical diagnostic report by the physician. Okay. Okay, this is the methodology that applied in study. So started with the data collection, and then we go to the data cleaning. Because of the medical image, usually the data is very limited. So, but deep learning need very huge of the data. So we need to increase the data by using data augmentation. So after we apply data augmentation, so we will have a better size of data set. So after we augment the data, we need to check the quality of the data. So we have several examples of poor output for augmentation, I will show later. And one of it is blur. So for the blur image, we will apply image reconstruction. Okay, after we apply image reconstruction, and then we have a complete data set lah. Okay, we have a complete data set is ready for the learning algorithm model. So we can proceed to the training the model. Okay, after we train the model, and then we need to find the best, can say simply said, the best setting for the deep learning. What is the best setting to get the best output? So we have several variables that we apply, or several settings for the model, and then we validate the performance using cross-validation or K-fold cross-validation method. Okay, from that, we can have the best classification model. Okay, after we have the best classification model, and then we take real data that we collect from hospital, in this study from Hospital Serdang, and then after we have the output, and then we also use a benchmark deep learning model, which is that a benchmark deep learning model is existing deep learning model developed by we can say verified good deep learning model lah, stable, robust and high level lah. So example is VGG19, VGG16 and ResNet50. So we train the model using our data set, and then apply or predict again using same real data from Hospital Serdang, and then compare the output from the developed model and compare with the benchmark classifier. Okay. This is the hardware software preparation. I'm using Google Cloud GPU, which is, I think you all are already familiar with this. Google Cloud GPU, it applies Jupyter notebook environment. So using Python 3 version, and then the backend is framework of TensorFlow and Keras. So for Google Cloud GPU or Colab, it has 12 GB RAM. And then the types of GPU is actually a shared resources. So it sometimes change, the types changes lah. So often available is K18, P4, and so on lah. Okay. Next, we go for the sampling design. Okay, for the sampling design, image or bone marrow image are from online source, which is collected from American Hematology Society Image Bank, and then we have pathology.outline.com and Medscape. All these bone marrow biopsy image are validated by the expertise. It has a description, and it has peer review by other doctors. So the disease is confirmed, and I mean the image is legit lah. Okay, and then for the inclusion criteria, the bone marrow biopsy image is from male and female patient. Okay, for the exclusion criteria, it must be not evolved or unevolved MPN, and it has no attribute to time period or geographic location. Okay, for the after we collect the data, then we need to augment, right? So for the type of augmentation, for example, we apply rotate, zoom, shift, and then flip. So the value setting is as you can see here. Okay, so this is the example of image that we augmented. This is, for example, original bone marrow biopsy from ET class. Okay, and then example, if we apply shifting, okay, it has like duplicated of the pixel here, and then example, we apply zoom, so image will be bigger and more focused, and then we apply rotate, image is like the last, and then flip and sharing. Okay, after we augment, we check back the data. Okay, this is the example of poor augmentation method, poor augmentation output lah. For example, we lost the surrounded features, but to analyze MPN, we need several features to to diagnose. But from this image, it has losses the surrounded features, so we need to ignore this picture. And then, for example, another example is blur image, and then another one is black padding and duplicated pixel value. So what happened to the poor augmented image? So for the undesirable image, it will be removed because the training process will feed to unclean input and give prediction with wrong output. So if you familiar with the concept GIGO, garbage in, garbage out. So if we train with the good data, it will produce good output. So if you feed with the unclean data, unclean image, so it will produce poor output or poor prediction. Okay. Okay, with a suitable image frame, the image is cropped to region of interest. So the image that we can save, so we can crop the image, then we can use it lah. And then for blur image, it will undergo
your voice ada ni.
process using SRCNN. Okay, this internet connection is unstable. Okay tak?
Sekarang okay. Umi cakap
okay, okay dah. Hello, testing.
Okay.
Okay. Maybe the internet connection. Okay. So everyone is okay? Can I hear voice? Oh, semua. Okay.
I'm not sure. Maybe only me still awake.
Still awake. So the rest?
Okay.
Alright.
Okay.
Alhamdulillah.
Yeah.
Okay. Alright. So okay. Continue. For the blur image, continue for the blur image. Okay. So blur image is undesirable effect that leads to the loss of necessary details required for the interpretation. So we apply Laplacian operator to calculate Laplacian variance, and then we can have the score of blurriness. So for the Laplacian variance calculated is less than 100, so the image will classify as blur. Okay, for the variance greater than 100, it's not blur lah. Okay, so this is the example of Dr. Syam.
Yeah.
Ada nampak yang ni kat atas ni ke?
Kat atas, which one?
Stop video.
Stop video.
Bukan. How to macam dia ganggu ni.
When you are sharing ke apa?
No. Okay.
Tapi tadi memang there is a problem because when I look at your video, your face, dia macam crop, dia jadi crop. So I'm not sure what happened while what creates the problem. I'm not sure.
Okay. Yang ni okay. Now
this one is okay.
Right? Okay. Alright. So this is example of output for calculation of Laplace variance. So we have the image in RGB, and then we change it to grayscale to see the age or the segmentation of the cell or mirror cell. So after we apply the Laplace variant, so it categorize the image as, for example, here is not blurry. So the value is 629. So it's more than 100, so it's not blur. For example, the blur image is here, example. So category is blur. The value for the Laplace variance is 70. Okay. If we see from the RGB, sometimes it cannot identify the blur image, but using the Laplace variance, it can calculate. You also can see from the grayscale, the image, the grayscale image for the blur image are fade, right? But for the good image, the segmentation is good lah. The age detection is better. Okay. Okay, for the blur image that we have detected, it will go through image reconstruction. So we will reconstruct the image using super resolution convolution neural network. Actually, the SRCNN actually. SRCNN is one of the deep learning model. So we apply deep learning in deep learning. Okay, so it will learn and mapping of low resolution image. So the blur image, it has low resolution. It will reconstruct to high resolution image. So as a result, image quality of low resolution that appear blurred can be improved. Okay, this is the architecture of SRCNN. So for the SRCNN, actually the main part, we have 4 parts lah. We have the pre-processing. We will upscale the low resolution image, and then we have the feature extraction, and then feature extraction to extract the features in the low resolution image, and then we have nonlinear mapping. Okay, for the nonlinear mapping, we will map the feature low resolution to high resolution, and then we finally have the output of reconstructed image. Okay. Okay. So this is example of after we reconstruct the image. So before the Laplace variance is 54. So the grayscale is, you can see it's almost like nothing. So after we apply the Laplace variance, after that we can see clearly actually what is the segment of the cell. Okay, so the model can learn better lah. Okay. Okay, after we have reconstruct the image, so we have complete and clean image. So in total, for 3 classes, we have 5,964 image. Which is balanced data set, meaning that for the 3 classes that we want to classify, we have balanced numbers of the image. Okay, and then for the we apply the data set ratio 70, 20, and 10. So for the training, we have 4,000 plus, validation 1,000 plus, and then for testing 500 plus image.
Okay, I have question, me.
Yes.
Probably, no, because probably they are not realizing it. Okay. Maybe they are not sure. Okay, why do you need augmentation, and then why do you need to do the you improve the blur image and you improve the resolution of the image? Why you do that in this project?
Okay, for deep learning, to apply deep learning need a very huge data set so that they can learn better. Example for neural network, or you can say conventional AI lah, using neural network, we can use like maybe 30 image is enough. So the model can, but it will at some point, the model cannot perform better. Let's say after we if we train or try several method or approach, the network will not perform any better lah. But if using deep learning, so the model can maybe achieve like 69 or maybe 69, 96% or it's better lah, better performance. But to achieve a better performance using deep learning, we need huge numbers of data. So in medical, for example, we have very limited image. Okay, because for the patient, compare patient data for like this, we have a bone marrow image. It's very little compared to nature image. For example, for tree image or car image or cat image or dog image that we collected. It's very easy to find. So we have huge number of the image. But for medical image, the data is very little. So to apply deep learning, we need a huge number of data. So that's why we apply data augmentation. So data augmentation is technique to increase the number of data set, to increase the data, so we can have a huge data set lah, so that we can apply to deep learning. Okay, second question dah lupa dah Doktor.
Okay, once you have data augmentation, I think probably the class have seen the errors or unwanted area created by data augmentation. So that's why Umi is performing the blurry tadi using the variance and also the resolution method.
Yes. Because to make sure the image that we feed into the deep learning model is clean data. So like I mentioned before about garbage in, garbage out. So example, we feed the model with unclean image or the image that blur and it has black padding, which is less features in it. So the model cannot learn in a good way of information. So it has less information that true to the classification lah. So after we apply blur detection and then we apply reconstruct the image, meaning that we improvise the quality of the image. So we improvise the quality of the image and then we feed better input to the deep learning model. Perhaps it can learn in better way, so it can predict. So meaning that the prediction of the output will be better. That's the answer lah.
Yeah, good. Okay, okay, class.
Question.
Yes.
You described now how the quality of the image will, how to increase it, but at the end, how you can make sure that it's really better before you start your training process?
Actually, I apply preliminary study actually using a smaller data set, like 300 image, and then I feed to the model, and then I can see the image performance is better when I reconstruct the image. So before it was like for the model that didn't apply image reconstruction, the output is like 80% accuracy. But after we apply the image reconstruction, output it can achieve like 90%, 90 plus lah, 90% accuracy. So it proves the concept of reconstruction image is good to apply lah in this in this study. Hope it answers.
Thank you.
Okay. Next. This is the input of bone marrow image. Bone marrow biopsy image. Okay, this is the clean image lah. Compared to the poor augmentation, we have the black padding, the blurriness, and then zoom. It's too focused, so cannot classify the best features lah. So from here, actually, from the literature, we know the features of the MPN. So from here, we can observe the discriminative features according to WHO. For example, we can observe the cellularity, the megakaryoparesis, example, the size of the cell, the cluster formation, nuclear features, and also the fibrosis. Okay, this is the architecture of the architecture of MPN. So this is the heart of the research lah. Actually, so for the deep learning, we have feature learning, and then we have classification. So for neural net, usually it consists of 3 layers lah: input, and then we have hidden layer, and then we have output. But for feature learning, that's why for the deep learning, that's why they call deep learning, because it has many layers. Okay, for example, it has convolution, and then it has max pooling, and then convolution again, max pooling again, convolution again, max pooling again. It depends. The architecture, it depends on how you construct it based on the variable technique that you apply lah. Okay, for example, we have the input image, and then we do convolution. Convolution, it has the mathematical function lah behind it. So it will extract details a bit lower level of the image. Okay, and then we have very high dimension, so we apply max pooling to reduce the dimension. Okay, after we reduce the dimension, and then we do a convolution again, meaning we will extract a bit higher level of the image, and then we reduce again the dimension. Reduce the dimension. The max pooling using the average, the maximum value lah in the dimension. It's a bit complicated to explain, but that is the concept lah. And then convolve again, meaning the higher convolution, meaning the model will learn higher level of image. Okay, after we have last layer of the max pooling, and then we do a flatten. Okay, flatten to it's like the dimension of image will become 1 times 1 lah. Okay, and then we have the fully connected layer, and then we apply dropout to one of the regularization method to avoid overfitting. Okay, overfitting is when the model cannot generalize prediction, meaning that you feed the model with the too specific information. So when you feed the model with another input, so it cannot generalize lah. So the performance is not good lah. Sometimes you can see the prediction is very high, but actually the model is it's not good lah after you apply several evaluation metrics. Okay. After we go to the fully connected, then we have the output for the classification for ET, PV, and NF. Okay. Okay, we have the basic structure, the architecture, but in the architecture, it has several parameters that we can tune, okay, we can tweak to get the best performance of the network. Okay, for example, here we manipulate the input size, 32 times 2, 64, and 128. We also apply for the epochs, numbers of epochs, and then the batch and optimizer. Okay, so each of these setting has their own function. So, but I don't want to stress out of the function. You can learn it later lah. Okay. Nanti lagi semua orang tidur. Okay. Okay. After we apply hyperparameter selection, and then we run again the model again and again for each variable. Then for each variable, we have the output, the accuracy, right? So for the output, for each model, we apply cross validation. So cross validation actually is a resampling procedure used to evaluate classification model. So for example, that we apply 70, 20, 10, like for the data split. But example, we only take stagnant ratio. I mean the apa ni nak kata for the macam nak kata pecahan of the data set
Divide.
lah.
Actually, we try
Okay.
to make sure that when we choose the test and training samples, we are not biased to, let's say, in training we choose all the good ones, a very easy
Yes.
one. So when you go to testing, maybe it's very complicated. So maybe because that complicated image has never been trained, that's why the model cannot understand or has no knowledge about that pattern. That's why the error will be, or the accuracy will be very low. So we try to create a variation of a batch or size data set, so that the model has experience of training the more complicated, more simple, I mean the variation of them. And then we will have variation of test sample images also. So to ensure the fairness of training and testing.
Okay. Yeah. Because for example, we have image A, image B, and image C. For example, for the first training, image A, image B, and image C in training set. Okay. After that, we revamp the structure of the data set. Then image A become in validation set, and then image B and C in test set. So it not necessarily every time you run image ABC in training set. So we change the position or the
Orders.
the orders of the image lah. So that every image have every image will run in different position lah. Easy to say.
Umi, I have question from the chat room.
Oh,
Kaka is asking about what are the difference between machine learning and deep learning in terms of feature extraction. Did deep learning perform feature extraction, or is it same as feature learning process?
Okay. Baca dia punya soalan.
Two question.
Chat. Okay. Different machine learning and deep learning. May I know? Okay. For different between machine learning and deep learning. Okay. The bigger concept is the machine learning and deep learning is under AI umbrella. All of these are artificial intelligence. Okay, all are artificial intelligence. So under artificial intelligence, we have another subset, and another one, one of the subset is machine learning. So machine learning under machine learning is deep learning. So meaning to say, deep learning is one of the machine learning. Okay, so deep learning is under machine learning umbrella. So in terms of feature extraction ni, we apply in conventional machine learning. For example, macam neural net, we will apply feature extraction. But for feature learning, the difference between feature learning and feature extraction is feature learning, it can automatic. We don't need to handcraft the method of feature extraction to get the best features. We just feed the image to the model. The model itself will apply feature extraction. Okay? Is it clear?
Yes, madam. Thank you.
Okay. Okay.
Yeah.
Okay. Next, after we apply cross validation, then we know actually which one is the best model. Okay. The best model is meaning the best setting from the hyperparameter that we choose before lah. Okay. This is the output that we apply hyperparameter selection. So we have numbers of number of box 50, 100, 150, 200, and also the optimizer Adam, RMS Prop, SGD, AdaMax, AdaGrad, The selection of the hyperparameter is based on the literature lah, the common setting that used. So we apply, then we observe using our own data set, so we can have the output may be different from the input, meaning that a different image will produce different output. So we need to try which one is best. Okay, so from here we can have for the number of epochs, the best number of epochs is 250 using ADAMAX. Okay, achieved about 94.72%. Okay, for batch, we achieved the highest here using 100 number of batch from ADAMAX as well. Okay. Okay, this is the final result for the classification output. So from the hyperparameter selection, so I've choose two best model, okay, to classify MPN. So the setting is for the input size is 64 times 64. So the batch is 50 with the number of epochs is 250. With the execution time is 5 minutes. The test accuracy is 95.45 with the loss 0.15. So you can see the training and validation graph. So this is, you can see like optimal learning lah. For example, for the overfitting and the underfitting, so we can see the process or the phenomena happen from the graph, training and validation. Also from the training and validation loss. That one you can study later lah. Okay. This is another evaluation matrix for the model, which is confusion metric. And then we have the precision, recall, F1 score. And then we have ROC. And then area under the curve, ROC, AUC. Okay, for the confusion metric, you can say for the total number of image per class is 198. So for ET, it able to classify 192 correctly. And then for MF, 184 and PV, 191. So we can see the less performance is to classify MF lah from the confusion metric. So from this, we know actually which class, which type of the disease that our model cannot predict the best. So maybe we can improve our image for MF, example, or maybe we can increase the number of image for MF only, but it become imbalanced data set lah. So we need to apply another method, another approach for that. For example lah, if you need to improve. Okay, for the precision, recall, F1 score, it's about the specificity actually, specificity, sensitivity, the similar concept, but use the different name lah, but the formula is the same actually. Okay, so this is for ROC and then AUC. So the best is when the graph is achieving 1 lah. Okay.
May ada question? There is question from the chat room. A long question. I don't want to read. You have to. There are 3 questions. Okay.
Okay. Good afternoon. I want to ask about model data set. What is different? Di panjang macam di satu kelas ni doktor nak explain ni. Between training phase, validation and testing. But maybe you can answer roughly.
Briefly.
Okay. Different between training, validation and testing. Okay, training and validation and testing. Okay. For the training and validation, during training process, train the model, but we need to also validate the training. Okay, it's different from the cross validation, but the concept is same lah, to validate the training, meaning that if maybe doctor can explain better for this training validation. I think I want to.
Okay. You can have. There are different ways, but the most essential one are training and testing. That is the most important one.
Yes.
But you also can have a training, validation, and testing, meaning that if you have 100% of data, you can divide it into 3 groups. So normally what we do, 60% for the training, 30% for the validation, 10% for the testing. So meaning that that's going to be decided earlier. Okay, so it's a default. You divide it or you randomly divide them from the start. What like Madam Umi is doing is she can have a training data set and that testing data set. In the training data set, it has rotation where it has that's why she is using k-fold. So rather than she divided them from the start, now from the training data set, she divided it into 2 groups and rotate as a training or rotate. It can be training or it can be a validation data set, so that it's going to be more fair, and you can have better model rather than you put choose that 60% from earlier decision or earlier selection without knowing what would the pattern will be. Is the model good enough or not? So it has a high risk. So if you have a low accuracy, maybe what happened is because the data that you train is actually very simple, too easy to model. So when you come in across a testing data that is very complicated, your model will fail to classify it because your data set in training is too easy. Okay, so we try to avoid overfitting, but we try to avoid underfitting. So we have to find the middle point here. So that's why we try to vary how we do the training and testing with inclusion of validation. So it's no right or wrong, as long as the training and testing is there and you're able to achieve good results for training and also test results. That is our goal. Yeah.
And
Okay.
for simply say jugalah, for the training and validation, usually they are in one data set. But for the testing set, it actually we can say unseen data. Which is the data is cannot be seen by the model during the training. So it's separated from the training process lah. Okay. Okay. Number 2 is, does the phase is affected depends on model, either scratch model or pre-trained model. Yes. Okay. For example, in this case, actually we can for my study I use a scratch model lah, developed from the scratch, and also I can use pre-trained model. So pre-trained model, so we can use fine-tuning approach and so on. This both method can achieve the same objective to classify the MPN. Okay, it depends on how you approach, but I don't choose pre-trained because I think it has too many parameters I need to control. So it's better for me. I know each one of the parameters that I use in my model, so I can tweak better lah. That's why I choose scratch model. But many study also from literature they are using model pre-trained model and also can perform better. Okay, and then for the third question, as the training phase only made for training purpose and validation for fine-tuning purpose, does pre-trained model need training purpose? Yes. And also, to train the pre-trained model, it has several approach also. Either actually yes and no lah, yes and no to train. Example, the pre-trained model that already developed to classify natural image. For example, to classify between dog and cat. We can use existing model, we load the model and then we put our image directly to classify. The model is ready to classify using pre-trained. And another method is we can use the model, the base of the model, but we freeze several layers of the model and then we train again using our own data set. So it has several approach lah. So the answer is, do we need training? If the model is similar case with your case study, no need to train. You can directly use. But for example, the approach is different, meaning that you want to classify between cat and dog, but you use this model to classify cat and dog to classify bone marrow. So it's not suitable. So you need to train again your model. Okay. Hope it's clear lah the answer.
To add on that, in deep learning, actually, when you are doing the feature extraction, more or less is actually you are trying to apply image processing filters to the image and try to emphasize or to extract the information from the image. So for example, if you have data, pre-trained data model that has been trained to for circular images, okay, so you have circular edges extracted during the deep learning process. But suddenly, when your image is actually more on rectangle, but the one that you have, the model that you have is on circular, but now you are trying to classify an image that are a rectangle. So the information extracted from the model will not be similar because circular is more on the radius, more on the edges, more on the size, more on the center, and yet rectangle is more on the information of your width and height of the rectangle. So basically, the characteristics of the image that you would like to classify must be related, then only you can use the pre-trained model directly. Okay. Next question, Umi. Ada lagi?
Next question. Based on your experience, what other possible approach that can be used to fix or reduce overfitting beside adjusting the data set and performing weight regularization? Okay, regularization pun we have so many approach. Batch normalization. I think try it first. Okay, another method is what another method, Doktor? Masa tulis literature tu ada baca tapi lupa lah. Jadi nanti boleh study lah.
This one is
Ada
overfitting You check on your data set, Kakak. Your data set has a variation or not. If your data set is having low variation, that's why you have the overfitting. So for example, if your image is to classify that Kakak, what is your problem, your data set? Probably you can give exact.
Classify the EEG, the brain signal.
Okay.
Perform classification, the time series data.
So classify EEG for what kind of cases or disease?
Not disease. To classify the imaging speech.
Classify imaging speech?
Yeah, based on the brain signal.
Oh, speech,
So it's not the speech. The data, the value is labeled with the word. So I need to classify the word. Actually, the word is the imaging speech that obtained from the
LSTM?
Yeah, I'm using LSTM, and then I got try another method, which is deep learning. I'm using the 1D CNN, but the validation accuracy remain constant, and then from the classification report, the percentage is also quite low. Yeah, and then the validation loss will also increase when the training epoch is higher.
Again, the last sentence. The
validation loss increases when the training epoch is higher.
Okay.
Are you already try the? Okay, you already try change the number of epochs.
Yeah.
Because my previous issue lah, I also face issues on activation function. Previously I use ReLU. Okay, to make it clear, LSTM is one of the deep learning actually. Okay. Okay, LSTM is under RNN.
Actually, I got a good performance by using the LSTM, but in terms of 1D CNN, the performance is not quite good.
Oh, okay. So, understand. So, the issue that I faced before is activation function. Commonly use ReLU, but after I use ReLU, the output is stagnant. So it not improved. The weight is not improved. So I changed to leaky ReLU. So after I use leaky ReLU, so the performance is perform better lah, because of the data. The threshold value is stuck when the value that they calculated become negative value. The weight is not updated. So I need to use another activation function. So maybe because this, I mean the problem is quite, I mean, we need to see in details because yeah, you need to see details.
So what you can do, Kaka, you reverse engineer, okay? You look at the errors.
From the back.
Look at the errors,
yes.
and then you look back until you see the data that you have. Probably the data that you have is noisy, or the features that you
Yes.
extracted is totally wrong. It can be the cause of.
Because doctor, you remember at the early of the study, I took everything. The image
Yes.
is very dirty image, and I put all together. So
Yes.
and it actually you need to apply pre-processing, even though they said feature learning is good to automatic extract the features. But actually you need to clean your data, but also you need to know what is the clean image for your data. Okay.
The clean
Sometimes you say,
signal. Yeah.
you need to know the signal is clean, but is it clean is clean?
Okay.
So you need to know lah. So the pre-processing, from the pre-processing, maybe effect from that lah.
So maybe if you have lots of data, you can sample all the data that give you error. You look at the characteristics, or you look at the value that you extract from the feature extraction value. Maybe from that layer, you can print it out and look at it. Maybe the pattern is overlapping. That's why you cannot classify them.
Yeah.
Huh?
Probably.
Okay, Kaka?
Yes,
Alright.
thank you, doctor, and thank you, madam.
Okay, welcome. Continue, slide tak habis lagi.
Oh, very good this week, because they ask lots of questions. Okay, Umi. Okay, you can continue, Umi.
Okay, so that one is model number one, which is the best model that we select after cross validation, the first model, and this is the classification output for the model 2. So the input size is the same, also 64, and then the batch number is 100, but the number of epochs is less. So does the execution time. The time is less also, only about 2 minutes. The test accuracy is 95. It's around the numbers also. So we can see the training and validation is quite optimal lah. Okay, and this is the training and validation loss. It's a bit apa ni orang kata gap lah. Apa ni little gap, but after that we evaluate further lah the model. Okay, so from the conversion metric, say the less accuracy to classify goes to PV. Previous is MF, goes to PV, but not much different lah from MF. Okay, and also for the precision, recall, advanced score, it's actually almost similar, the performance. And then for this is the RC curve, and then the AUC. Okay, after that we try to predict to classify the image from real patient data from Hospital Serdang. Okay, so this is the output. So previously the accuracy can achieve up to 95%, but after using real data, so the accuracy goes to like 85, around 87%. So it's expected actually when you use real data, so the performance is getting lesser. So okay, but it's still in acceptable range lah. Okay, this is the classification output. So in this real data, we are using 300 of image. So each class we have 100 image. Okay, so for ET, it can classify about 85, MF 81, and the best is PV. Okay, for the model number 2, the best to classify is ET 92 here, and then followed by MF and then PV. Okay. Next, okay, this is example how we predict the image lah. Okay, in this model, for the apa dipanggil we are using softmax to predict so for the softmax, total prediction is equal to 1. For example if for binary case to classify cat and dog, the prediction output is maybe the threshold is 0.5. So below than 0.5, classify as dog. Above than 0.5, classify as cat. Okay, but if for multi-class, it different. So it doesn't matter the partition of the data as long as when you sum up the prediction, it becomes 1. Okay, for example, here you can see MF here is 1, but actually 1.0000 something lah. And then when you sum up, it's become to 1 lah. Okay, so when we feed the image, and then it give the output, predict the output. For example, this is image for MF. Okay, MF underscore blah blah. This one is only label lah. I used to label the image, but the image is belong to MF plus, so it predict correctly for MF. Okay, example for ET, this one lah, ET, and then the value of prediction is 0.9 something, so it correctly classified, so the classification is true lah. For example, we also have misclassified. So example for misclassified here is example this image is belong to MF, but 80% this model predict as ET. Okay. And then example for this ET image, but it classified as MF. So maybe lah when you see the image also, maybe that's why I mentioned about the interoperability between the physician and the doctors, right? When they observe, sometimes they say, oh, this is MF. No, this is ET. Because sometimes you can see it's like MF, sometimes it's like ET. So we need objective tools that can help them to classify the image. So this is one of the approach to apply. So we have numbers that no one can argue about the numbers, right? Okay. This is an example of the output lah. Then, okay, after we develop our own model, then we want to compare the performance with the pre-trained model. Pre-trained model is the existing model lah, that already verified stable model. So the step or the approach that apply here, we have several methods also, but this is method that I apply, which is I train again the model, but freeze the top layer. Okay, freeze the top layer is the classification layer lah, to map with my own case study. Okay, so first I need to select the pre-trained model, and then I create the base model. Create the model is actually download it from the using API. So download from the library lah, and then code to freeze the layer, and then train new layer on bone marrow biopsy dataset. Okay. So this is the final output. Compare the performance between model 1, model 2, and the pre-trained model. So for the CNN model 1, it can achieve about 85.7. Model 2, 86.7, the previous result lah. but for the VGG19 is better lah, about 81. And then VGG16, 79.7. And then the lesser lah, the lesser is 76.3 by ResNet. So I also actually perform another evaluation metric lah. I don't know, but I didn't put in here lah. I put in my thesis. Okay. Okay. And then this is the comparison for the loss, and then the accuracy by subtypes. So we can see lah, some of the model can classify some class better. It depends on, sometimes you if you want to focus on one class, so maybe you can apply that model. So you know which model best perform to the certain class. Okay, so okay, for the conclusion, first is distinguished morphology of bone marrow biopsy was identified from WHO guideline. And then deep learning algorithm can be applied, it's proven to be applied to classify 3 types of MPN with appropriate hyperparameter tuning. So it can achieve the accuracy 95.45 for M1 and 95.29 for M2. This is from test data from the first step lah, not output from the real data. Okay. Performance of the developed model was assessed by the evaluation matrix, the advanced score and everything. And finally, the finding of the study was validated by comparing the detection output with the clinical diagnostic report by physician. And we know that M2 surpassed the performance with 86.7, followed by M1 and then VGG16 and ResNet. This pre-trained model, I'm not denying that they can possibly perform better also with appropriate fine-tuning. But this one I only apply freeze the top layer and then train again. I can do it again, but that one become another thesis lah. So I just train for the one set of the fine-tuning lah. Okay, that's all. So Q&A session, it depends. You can ask about my study, and also you can ask maybe you have target to work as data analyst ke, data scientist ke. You can ask also. Okay.
Hi, Madam Umi.
Yes.
My name is Lukman, and I have a few questions.
Oh, okay.
It may take a while. I have experience with K-fold. Actually, I'm using it for my final year project.
Okay.
I would like to ask how common is it in the real world professional use? Do they use K-fold? Like how common do they use K-fold? That's the first question. My second question is, what happens if the validation accuracy is higher than training, and how to prevent it? And is it okay if the testing accuracy is higher than validation and training accuracy?
Okay. Okay, that's all. Okay. Okay. How often we use K-fold? K-fold is I can say dah macam move to forward from the process. I can say macam nak kata K-fold, when you apply machine learning, usually you will apply K-fold. Okay, for example previously but that one I use clustering. For clustering, I'm not applying K-fold because it apply different method to validate also. But meaning to say that K-fold is one of the validation approach. And another method for clustering, example they apply self-weight analysis. Both are validation method to the model. So what I want to stress out is validation is must. Validation is a must. It doesn't matter you apply K-fold ke self-weight ke, as long as you must apply the validation. So it must lah. It's not often it must. It's a must process. Okay, and then second question is validation is higher than training. It can happen. When you train, many possibilities happen. I also experienced for this one. Validation is higher than testing, but usually I don't believe this model lah. If the validation is higher, there must be something in your data set composition. So check back lah. And also same with the testing is higher than training. Sometimes because of the proposition of the data, when your training set is easier to learn rather than in training. So that or the either way lah, the testing or the training, meaning that the distribution of the data is not balanced lah. So the model more easy to predict the testing data. So it become higher accuracy. So also actually issue. So you need to check back lah. But sometimes it can happen in a good way, but actually you need to check back your data, the data set lah. Okay.
Thank you, Madam Mu. In terms of checking back the data set, what does it mean specifically?
Meaning that you check back, example lah for that one, is it the data is already clean, and then sometimes because of the imbalanced data set, not every problem we have, we can collect balanced data set, meaning that example we have 3 data set kan, not necessarily we can collect 100 image for class A, and then 100 image for class B, 100 image for class C. Sometimes only 50 are available. After we augment, if we augment 50, we need to say less image, but we over augment. So the variability of the data is less for the class A. So actually the model didn't learn better for class A. It also can cause overfitting. So meaning that check back your data lah, either imbalance. If imbalance also can cause performance, can affect the performance lah. Banyak lah the reason. So meaning that check that the cleanliness of the data, and then the distribution of the data, and then how you process it each, because sometimes you apply multiple approach to process the data, also can meaning that over effect to the image lah, or the data set pun boleh jadi juga.
Luqman is doing image kan, Luqman?
Yes, Doctor.
Okay.
Not much different from Madam Umi.
Okay. So
but mine is on not in medical punya area lah.
so do you have augmentation?
Not really, Doctor.
Oh, you don't have augmentation.
Yes, because I think my data is clean enough, and I distributed it with equally using certified. It's just that I don't know what's causing it and how to prevent it.
Okay.
Oh, so you have testing and validation higher than training lah.
It depends on the model juga. Usually yes.
Some got higher, some got less.
Yes. By higher I mean it's like less than 0.5% of difference, like 0.3, 0.1.
Oh, very less lah. Okay.
Yeah. So is it a big issue that I have to take concern with?
Lecturer kena jawab.
Normally it's a big concern lah, because theoretically the one that you train should achieve the best accuracy or the least error ever compared to validation and also testing. Especially testing is totally unseen data. So how is it possible your model is able to classify your testing higher than training? That is totally, like
acceptable lah actually.
Yeah. You teach your model to recognize letter A, but suddenly when you test with the hashtag, or probably the alias symbol, suddenly your model able to recognize that as a, or maybe as alias or hashtag. So you never teach that model that character. So magically or mathematically cannot be derived. So what you can do like Kaka, you go backward, reverse engineer balik, look at your confusion matrix, which class contribute to that error. Maybe that class, then you look at back at your image contain what are the characteristics that you want to highlight. Maybe that characteristic too big ke ataupun too significant or too obvious. That's why uh, test can classify, or maybe it's vice versa. So you have to check back. Okay. It's
Right. Thank you.
okay.
That's
All right. Thank you, Lukman, for 3
Mm.
questions. Very good. Normally
Okay.
dalam my class in my class they don't ask question.
Oh.
So I think today's session they got lots of questions in their head, right? Okay.
Okay.
Other than the rest, do you have any other? Okay.
I think let's check
Okay.
in.
Bernard asking about how do we decide on the number of neurons in our model?
Okay, to decide number of okay, in deep learning lah, usually we set for example we have 256 512, right? Usually formula I have the basic structure, yeah, like for input and hidden layer. I have the basic structure, and then I try run it to get the output lah. But also we have we have approach to automate this process. Apa tu nama dia tu? Graph bukan apa dah tak ingat lah.
Yang
We have the process to automate this method when we apply grid search, and another one also I forgot. I applied both method also, but this one huge, meaning that consume very high computational power, so that and very long, so I don't use this method. But this is one of the approach how you can determine a number of neuron or number of input, the layer and everything, using that approach. So you can handcraft, meaning that tweak the hyperparameter or testing with the several numbers of the variable numbers lah, testing manually, or either you can automate, example using the grid search, and another one I forgot. Depends. You can automate or handcraft lah.
normally we call it optimization of neural network. Yeah, it's actually a PhD work lah if you do that optimization of neural network. So for undergraduate, what you can do is if it's a non-linear, so meaning that you have to distribute your data set first, look at the pattern, look at the data distribution. If it's non-linear, obviously you need more than one neuron at the hidden layer. One is because it's non-linear, and then from there you grow or you add up the neuron and play with the activation function also until you get your targeted results. But the best thing is to look at the distribution of data. I think last week Dr. Sharifah already mentioned that when you look at data distribution, then you can see there are outliers, you can see that there are noise, whatever information that shouldn't be in the data set, so that it will not affect your ANN model. Okay. Good question, Bernard. Okay, the rest. Master students are here also. Okay,
One more.
one more. Okay, yes.
Tengah typing kot.
Because the his mic is having problem.
Oh, okay. Okay, during typing, anyone want to ask question?
Maybe master student Siva is also doing machine learning for his master. Who else? Yeah, in the yeah, Siva, do you have any question for Madam Umi?
Evening,
Maybe?
doctor, and Umi. There was a
hi,
great
Siva.
presentation and research has been done, and I've learned a lot from
Thank you.
here. In
Thank
fact.
you.
And the most important thing is I think I've not have reached this level because this is one neuro. However, most important thing I picked up now is cleaning the data set is the one which makes the other part, moving part, good level. I'm actually at the data cleaning at the moment, and thank you for the great knowledge today shared together. Thank you, Doctor, and thank you, Madam Umi.
Thank
Okay,
you.
thank you,
You can
Siva.
apply.
Yeah.
Thank you.
Doktor
Bernard,
one more tak keluar-keluar. Doktor one more.
what is it, Bernard?
Oh, okay.
Can I refer based on the number of features I have?
Macam tak ada kaitan je. It's not related to each other, right?
Yes, it is not. Number of inputs is the number of data that you have. Features is representing one data. So if you are talking about your coefficient, because Bernard is doing the speech recognition, so so he extracted the waveform and so get the features using represented by MFCC. So 12 coefficients to represent one signal or one data.
Okay.
So I think your question is saying that if you have 12 features to represent one waveform or one input, so how many input that you have is the number of samples that you have. Is it clear enough, Bernard? So they are not
not related, like I say,
not
number
related.
of input. The input nodes is not related to the
features,
number of features.
Because you already do the feature extraction beforehand. It's not in the deep learning. It's not in the neural network punya model.
Okay. Example, if you have, because common number of nodes apply. Example, we have 512, apa ni, 256. But it's not necessarily your features is 512 to 256. Not necessarily. So across some reference, maybe there is another further explanation put about this. The reference.
Okay, next question from Jiang Feng. How do you make
sure the training data is enough to get the model? Firstly, formula from literature. Usually, when people apply that model, how many data set in their study lah. For example, for previously I use for neural net, it's very less data lah, very less. I think about 100. So usually people put just use around that amount of the data. But if I want to apply deep learning, the data usually 1,000 of image. So from literature lah, you will know the numbers of the data set is enough or not. Other than that, you observe from the training lah. After training, you can see like overfitting. So you can know that maybe the model is not fit with not enough image from the evaluation matrix. So you can observe that. From literature or from the evaluation matrix that you do.
Is that answering your question, Jiang Feng? All right, thank you so much. All right, I believe, is there any probably last question before we can have a photo shoot session?
I have one more question.
Yeah, Lukman.
Let's say, for example, my training accuracy is higher than my validation accuracy, but my test accuracy is higher than training accuracy. So should I check the test result, the test data set, or is there any other way?
Meaning that your first when you do data collection, and then you make sure all the data is related to the case study lah. So that all the data collected is clean and good data. Okay, then you separate it to the training, validation, and testing. But during the training process, the folder is separated from the training and validation. So when I say that you need to check back the data too, not because of the, so the reason for the testing is apa ni, if you already confirm all the data set, so you know it's not related to the image that using in the testing lah. Unless masa you divide the testing, training and the validation tu, you pilih the only good image for the testing, sebab nak make sure the testing is good. So that one tu baru kena check, meaning that how you pick, so you kena randomly split the data lah.
Yes, my dataset is randomly distributed for all training, variation and accuracy, and also distributed equally for every classes.
So the performance happen in all that iteration.
It's before that.
Once lah, dia bukan all the time. Let's say you try 10 times, so 10 times tu dia reshuffle all the images 10 times differently.
Okay.
Not like that. I mean that I set up my dataset. Let's say I have 6,000, and then the program will distribute it to training how many much, validation how many much, and test how many much, right? And then use scaffold like just like a normal scaffold. It's just that I distributed it equally for every classes. Did I make any sense?
But the distribution of data will keep changing every time you rerun the program.
Oh yeah. Especially for the test.
Especially for the test.
Yes. For in between the fold is the same, but for the test, the test they change a bit. Let's say if I set it to 10% for testing, sometimes it for 490, sometimes 492, sometimes it's 489.
Okay.
But memang ada, because also happen to me also, masa preliminary yang 300 image kan, and then the testing is better, but I suspect this happened because I purposely pick the best image for the data set lah, for the testing pun yang memang cantik je. That's why so the testing become a good result lah. Maybe, but also maybe you can try early stopping. Ada apply tak early stopping dekat dalam training? Early stopping tu, so you can also one of the method to avoid overfitting lah. So the training process will stop just before the weight of the model tu akan achieve to overfitting. So can apply early stopping. So and then test the data again. Tengoklah dia ada beza tak.
Thank you. For the early stopping, is it for every? Do I have to put it for in each fold or for the entire
masa kita
training?
Macam model.fit. Lepas tu kan ada dia punya argument tu, then we apply early stopping inside the model.fit tu. Never mind. You can ni lah cari dulu model early stopping for the model.
Alright, it's just that I never use early stopping in K4 before.
Probably.
That.
Luman, how many data set do you have? How the sample size?
Close to 6,000.
Oh, okay.
Yeah, banyak sangat.
Because
Okay.
orang wearing mask or not wearing mask kan, Luman?
Oh, okay.
Wearing mask correctly, wearing mask not correct.
Okay. You have to check yang wearing mask not correctly. Is it not correctly at all ke, ataupun yelah wearing mask not correctly here,
ada gap between
here
nose
and here
the mask.
yes.
Yeah, there's a mix of tak tutup, not closing their nose. Some picture not covering their chin. Some not covering their chin and mouth.
How you classify or the cut off between the
Wearing
pakai
properly?
mask properly and not properly. There is a gap between you buat segmentation to predict the mask, and then you calculate the distance between mask and eyes ke the nose ke.
No, I just straight
Label lah.
label it and then put it in the network.
Oh.
Okay. I think you have to go to basic lah. Check back your data set. Do you classify or label them correctly? Sebab this is what I encounter with Amir juga. Before we do before he runs the punya deep learning, basically we go back to our data set. We clean up the data or this kind of images. Dia memang 50-50. Even us pun cannot classify. How can you expect the machine to classify? So we disregard that kind of images. So we call it data cleaning. We try to make sure the data that we insert are totally able to be classified correctly or significantly or not. Okay, so probably there are cases that 50-50. That's why classifier tu masa training it thought that this is not wearing properly, but dekat testing tiba-tiba dia kata okay, this is like not wearing properly but also like wearing properly. So dia that's why the decision to confuse the model, they confuse. So those are the probably the reason for your misclassification ataupun overperformance lah, your testing overperform compared to training and validation. Yeah, Luqman.
Yeah, understood.
Okay.
Reducing the number of epochs may help also.
Not necessarily. It depends on your training.
Okay, alright.
You
have to try and error.
Thank you for the feedback.
All right. Thank you, Luqman. Others, I'm not sure if others you have question or not, because you may involve with deep learning project for AI this course, since I already asking you for the proposal by this week. Yeah. So I assume if you don't have any question, we can have a photo shoot. Umi, maybe stop sharing so that I can request everyone to switch on the camera. Okay. You may contact Umi, Madam Umi. I will give. Boleh Umi? Can they email you?
Boleh.
Okay. I will contact. I will give Madam Umi's email in our WhatsApp group. Okay. So that you can ask further question if there are anything. Okay, switch on your camera please so that we can have a photo shoot. I think we have.
Can I get in, Doctor, on my phone?
Okay, boleh. Anyone need more gadget to log in? We'll have two screen, so twice tau.
Okay.
Luqman, where are you, Luqman? Last week we forgot to do photo shoot kan?
Oh.
Let me stop recording first. Kalau tak